Morning, everyone. So I just wanted to show you some of the tables that we have for this KSP section of the course. First thing I will do, I'm going to have two main tables that we look at. First one here is going to be the solubility chart. We've already used this a little bit. Just a reminder here again, everything would dissolve to a certain extent. They just arbitrarily say if you manage to dissolve more than 0.1 moles for a given liter at 25 degrees, we're going to call you soluble. Otherwise, we're going to call you low soluble. First thing I would do is I would actually look on this chart here, see if I can answer the question. Sometimes I could ask you the question, hey, between these four salts here, which one is most soluble, which one is least soluble? Sometimes you can answer it just based on this part. If I find the combination here, let's say for example, alkali salts with anything are always going to be soluble. Those are always going to be aqueous when dropped in water. If something is low soluble, let's say silver with chloride, that combination is low soluble. I'm actually going to put solid, right? Sometimes you can answer it directly from here. As you start going down on the table here, you start getting less and less soluble. We started seeing that sort of net ionic practice here, and also selective precipitation as a technique. What I also want to show you is one page over from there. If you can't quite answer which of these salts are the most soluble or least soluble here, you might look towards the next table, which is actually the solubility product constants. This is the new name that they gave for KSP. At the end of the day, this is a KEQ. Also, it's given at 25 degrees. So they give you a handful of salts here, maybe about 20 compounds there. It's all alphabetized for you here. For the salt, they actually tell you the KSP constant. So this one here is actually the equilibrium constant. This is KEQ. This one here tells you the products over the reactants. And what I want to just observe in general here is you notice that these KSP, all of these ones here are all 10 to the negative a lot. The K's here are going to be a lot tinier than 1. That means reactants are favored. Remember when we defined this KSP stuff here, remember we always had the solid on the left side. We ended up getting the dissolved ions on the right-hand side here. Even if I was mixing solutions where the solid was actually a product, I still put the solid on the left side before I define the KSP. If this ratio here heavily favors the reactants, that means we have very few ions. So as a general rule here, any one of these ones here, all of these guys here are low soluble. If they were actually on that first table here, they would actually be categorized something like this one. Oh, it's a combination, it's low soluble. All the salts that I currently give you are going to be low soluble. And what I can do here is I can actually make a correlation here. Let's take just a generic salt. Let's call it an AB2 salt. Right? An AB2 salt here, put the salt on the left side. First thing I would do is I write out the equilibrium. I get A as a +2, and I get 2B minus. I'm going to write out my KSP expression, which is the product concentrations A plus 2 times it by B minus with the squared. Remember, the numbers go up into the coefficients. We have a situation where the KSPs of all of these are small. Well, if KSPs are small, that means the amount of ions, we have very less ions or few ions. Well, why do I have very less ions or few ions? It's because this salt here is not very soluble. So not very soluble. So we came up with a conclusion last day here is, yes, I know in general all of them are tiny. In general, all of them are low soluble. But we have this correlation. If I have a higher KSP, a bigger KSP will come from the fact of having more ions. More ions will come from the fact if the solid is managing to do the forward reaction more. Increased KSP means increased solubility, more soluble salt. Still overall low soluble because these constants here are relatively tiny, but if you take a look at the numbers, you can say, well, something that's 10 to the negative 37 is way low solubility versus something that's only 10 to the negative 5 here. The KSP is relatively larger, even though I would still overall call it as a low soluble. It solidifies out. It's actually more soluble than something that's lower KSP. So let's just do a quick practice question here. Very common for a multiple choice situation. They're just going to give you a couple random salts, just as an example here. I want you to tell me between the following. I have Na2S, I have strontium hydroxide, I have calcium sulfate, and I have MgS. Right. I want you to tell me here, between these four salts here, which salt is just a generic ionic compound, which salt is least soluble? So if you just sort of translate that for yourself here, least soluble means here it dissolves the worst, right? Dissolves very poorly. Dissolves poorly. based on what I've said so far, we're looking for the one that has the smallest. I know all the KSPs here are tiny, but the one that has the 10 to the negative biggest number, right? When you're trying to answer this question, even though we will eventually probably need to look up the KSP table, I want you to start off looking at the solubility table, because sometimes you can just narrow it down some answers I don't even need to look for. So for example, let's try to find sodium sulfide. Let's look on the first table. Let's see if I can answer my question. Well, sodium is an alkali salt. Currently here, when I have sodium with sulfide, Na2S, that salt there is soluble. If they're asking me which one's going to be least soluble, well, this one here is aqueous. That's not even going to be in contention. That's going to be really soluble. In a very similar fashion here, strontium hydroxide. So hydroxide, OH minus, strontium hydroxide is also soluble. So again, I can sort of narrow down some of my options. There's no point in even checking those ones because you're looking for the one that dissolves the worst, and both of those are fully soluble. How about calcium sulfate? For calcium sulfate, always check this first chart here. Okay, calcium sulfate is a potential, right? It's low solubility here. That one there is potentially, so we have low soluble. That could be one of your answers. And let's just check it against MgS. We have our MgS here. Oh, this one here, easy. Magnesium and sulfide here. This one here is also a soluble combination. This one is aqueous. I didn't even need to check this added feature, the tiniest KSP. In fact, 3 out of the 4 are actually going to be aqueous, so that only leaves me with one choice. So even though at the end of the day you might need to compare KSPs, sometimes you can narrow down your answer just with that first solubility chart. Let's make it one step harder here. So we have CaSO4. Let me add one more to the list here. Let's add here SRF2. Okay, so let's say this was also part of the question here, SRF2. When you check the chart here, you're going to say, I don't have an F minus here, right? I don't actually have it on the table. This is not an exhaustive list, right? They just started giving you a ballpark here. If you can't find an answer on this table here, it's at that point then you check the KSP table. So in this case, if you find it on this table, great. I have SRF2 over here, and the KSP is 10 to the negative 9. So between these two, both of these would be referred to as low soluble. The calcium sulfate was actually on the first table. The SRF2 is on the second table. Because this value here is tiny, I know it's low soluble. At this point here, I want to check KSP roughly. So what is the KSP of the calcium sulfate salt? It's alphabetized for us here. Calcium sulfate is 7.1 times 10 to the negative 5. 7.1 times 10 to the negative 5. For strontium fluoride, the same KSP at the same 25 degrees is 4.3 times 10 to the negative 9, right? Now, usually, right, we had said, well, the bigger the KSP, the more soluble. If you want the one that's least soluble, you want the one that's smallest KSP. Usually, it's going to be, easy, 10 to the negative 9 is smaller than this one. This one here is low soluble. Okay, that will usually be the best answer. So both of them were classified as low soluble, but this one is even. This is the least soluble one. This one here is expected to be the one that dissolves worse. Now, there's one technical note here I'm just going to hint at right now. You need to be careful that these two salts here are not on a level playing field. If you take a look at the calcium salt, the CaSO4 dissolves to form Ca plus 2 and SO4 minus 2. When you get the KSP expression for this one here, it's just the calcium times the sulfate. Let's do something similar for the strontium fluoride. The strontium fluoride is like my AB2 type salt. I'm going to have strontium ions and 2 fluoride ions. You notice that KSP value here is actually strontium, the fluoride, but it's also squared there. So although in general, yes, it is true, the smaller the KSP, the less ions I'm going to have. Because this one here actually has a square, while this one here doesn't, it's possible that this number here may actually be tinier because of the square, not because it's actually more soluble. So in this case here, what you would need to do to really compare which one is soluble, what I want to do is I actually want to do the solubility. Solubility is a number that goes beneath the solid here. It tells you how much the solid dissolves. Let's imagine going x, x, and x. It's in a 1-to-1 ratio. Whenever you have placeholders for the ion concentrations, you can plug them directly into the KSP expression. So let's go here. This is going to be x times x is supposed to equal my KSP of 7.1. I had that number from earlier, 7.1 times 10 to the negative 5. What's the x, which is the solubility? X for the first case, so I didn't leave myself enough room there. The root of 7.1 e negative 5, x is 8.4 times 10 to the negative 3. Right? Always go back and reread the question. What were they after here? They were interested in which one is least soluble. You've now found that the molar solubility for calcium sulfate is 8.4 times 10 to the negative 3. What about the other case? Again, I don't know how much dissolves, just put in x. X and 2x, it follows a mole ratio. Anytime you have these two statements here, you can plug it directly into the KSP expression. This one here is similar to last day. We're going to have an x for strontium, a 2x all squared. That's going to end up becoming 4x cubed is equal to this 4.3 number we got from the table. 4.3 times 10 to the negative 7. 4.3e negative 7 divide 4 with the cube root. This one here, the x, how much is actually soluble is actually 4.8 times 10 to the negative 3. Okay. Again, go back and reread the question. Well, x was the molar solubility, was how much of the strontium fluoride that I managed to dissolve. You'll notice here, this is very curious, we had a generalization. The smaller the KSP, the lower the solubility should be. But it was because of this pesky little square here, you actually find that the solubility, wait, this number here is tinier than the other number. It's actually this number that actually guarantees, yes, very much so, the strontium fluoride is less soluble than the SO4. And I even factored in that problem. Well, they're not on a level playing field. One of them has a square, one of them doesn't. But no, this number here still is tinier. We'll see an example later on that, yeah, we're going to have a situation where one KSP is actually tinier, but it's only tiny because of the square. In fact, maybe the other solubility was actually a little bit lower. Okay, so just hinting at some of the problem styles here. I'm going to give you one more question just to practice, and then we're going to switch over to do what's referred to as a maximum solubility. Right? So just for practice, I want to do here a 150 milliliter saturated solution of CaF2 is evaporated to dryness. Sounds kind of strange. Okay, it's evaporated to dryness and weighed. I find the mass and weighed to contain 2.5 grams. I want you to find or determine the KSP. All right? So that's how this question is worded. Let's see if we can start off with the picture if we can. We're starting off with a saturated solution of CaF2. I'm starting off with 150 milliliters. That word there, saturated, is a hint that this is in equilibrium. We know that at equilibrium, we have a bunch of solid present, and we have the maximum amount that's dissolved. I've hit that saturation, that solubility limit there. Okay, so I have 150 milliliters of the saturated solution, undissolved material present. Then what I do is I evaporate to dryness. When I evaporate this one here, I'm always going to assume that water has a lower boiling point. So basically all the liquid escapes, all the solid is going to be left. So stick it above a hot plate or something, a coil of some sort, and basically I'm going to evaporate off all the water. I'm going to just have the mass of the beaker here, and basically I'm going to have just the solid left over. I find that there's actually 2.5 grams of CaF2 in my saturated solution. That 2.5 grams here partially is going to be some of the undissolved material present, but I'm going to imagine I had just hit saturation. This 2.5 grams is a sort of amalgamation of some of the solid there was, but also the ions that have recrystallized back out. Now that there's no water, it can't be dissolved anymore. Now in total, I have 2.5 grams in solution. So this actually describes for us the solubility. If I imagine that this is the perfect amount when I first hit saturation, you actually manage to dissolve 2.5 grams per 150 milliliters. Right? So that's the maximum amount that you can dissolve. So let's start off with the solubility here. Let's find the molar solubility. Let's re-express the solubility in terms of moles per liter. So we're going to have, currently it's 2.5 grams. I have it divided by 150 milliliters. Because I know later on it's going to be moles per liter, I'm going to convert this here to 0.150 liters. And again, anytime I have grams or I want to get to grams, you need to go through the molar mass. So let's go to our periodic table here. Let's find the molar mass of calcium fluoride. 40.1 plus 2 times fluorine is 2 times 19. So 78.1 grams for a given mole. 2.5 divided by 0.15 divided by 78.1. This one gives me here the molar solubility as 0.21 molar. That's the concentration in this solution. That's how much has managed to dissolve, 0.21 molar. Or you can say in words, I have dissolved 0.21 moles per 1 liter. Right? I didn't actually dissolve 0.21 moles because I don't quite have a liter, but at least by ratio. That's how much dissolved before you hit the saturation, before you ended up hitting equilibrium. Right? Remember, at any given point, there's always two ways of making a saturated solution. One way was mixing. You need to deal with the dilution. It doesn't follow the mole ratio. The other way is starting off with a solid. That's the easier way. If you identify which one here is your solid, imagine, starting with CaF2 out here, right? I have 2.5 grams of CaF2. I start tossing it into the water until it saturates because I'm actually dissolving a solid. So we're going to make an assumption here. Assume we're actually dissolving solid. And the nice thing about that is, great, it's going to follow the mole ratio. It's going to obey the coefficients in the stoichiometry, right? If I know what the salt is, in this case here it's CaF2, I'm going to put the solid on the left side. That's my solid. It's going to break out to form calcium ions and 2 fluoride ions here. I'm going to write out the KSP expression. These are two things I would write out for every single question. Once you know which is the precipitate that might form, write out the equilibrium and write out the KSP expression. Solubility is a number that goes to describe the salt. The solubility this time is 0.21. Because I'm under the impression of dissolving a solid, we're going to follow the mole ratio. So it's a 1-to-1 ratio. You actually dissolve 0.21 calcium when the liquid was still there before you evaporate it off. It's a 1-to-2 ratio. So if I take this answer times 2, I'm getting 0.43, give or take a little bit of rounding there. Because it follows the mole ratio, great. I now know how much calcium ion. I now know how much fluoride ion is in the solution. Now what's going to happen, anytime you have these two numbers, the placeholders at equilibrium, we know we're saturated, you can punch them directly into the KSP expression. And as you do that here, the KSP is going to equal to 0.21 times it by 0.43. Oh, I've already doubled it. Do I have to square it? Yes. Okay. These are two totally separate equations. So you just punch through the math here. I have the whole number here, 0.43 squared, times it by 0.21. Again, give or take a little bit of rounding. I now found I'm at a temperature where the KSP is, my calculator just gives me 0.038 like that. On your KSP table, it probably written 3.8 times 10 to the negative 2. Okay. In general, this number here is very tiny, right? So overall, we can say it's low soluble. But as compared to some of those other KSPs that we had, 10 to the negative 9, 10 to the negative 37, something like that, this one is relatively more soluble than the other ones here. And here we have a nice case in point here. I want to show you, yes, solubility actually goes with the solid. It tells you how much dissolves. KSP also tells you something about how much dissolves, but you see that numerically they're actually different values. So even though they're proportional, even though in general this is a relatively big KSP, it means it's relatively good as a low soluble salt, these numbers are not the same. So it's fair game for them to be like, here's some information for solubility, find the KSP, or vice versa. If you know the KSP on the table, can you backtrack and end up finding the solubility? That's when you use your X's again, very similar to what we did with the molar solubility in this question here. Okay? So although they are related, they are numerically two different values. One other setup I want to introduce you this time, just a couple little spin-offs to the unit so far. This one here is going to be worded as, can you find for me the maximum concentration before saturation? Again, we're looking at a few problems here. I want to just highlight right from the start here, sometimes they refer to it as a maximum amount. This is how much you manage to dissolve before it starts solidifying out on you. You can also frame this here as minimum. Well, wait a second. Maximum, minimum are something totally different. But what if I frame it as the minimum needed to reach saturation? Right? So either you think of it as a maximum. This is the upper limit. This is the most ions that you can dissolve. Or I can word that as the minimum, how much do you need to add until the saturation happens? Notice that they're asking the same question here. Okay, so let's just try out a problem here. I want you to find out for me here what mass of strontium chloride can be added to 15 milliliters of 0.750 molar sodium carbonate solution. I'll give it simpler for you here, before saturation. Right? In general, well, there's no limit. You can toss in as much strontium chloride here. Well, the limit is going to be saturation. The limit is going to be you only have 15 milliliters worth of liquid. There is going to be some upper limit. Even if it's something that's fully soluble, we're going to eventually hit some saturation point. You've completely maxed it full. So let's just try off here. Let's start off with a picture. Currently, I have 15 milliliters. The concentration is 0.750 molar, and we're talking sodium carbonate. Now this one here, sodium salt, is going to be fully soluble. Even though I label it Na2CO3, I think of it as Na plus ion swimming around by itself, CO3 minus 2 ions swimming around by itself. In a similar fashion, what I'm going to do is I'm going to start dropping in some strontium chloride. I don't know question mark grams, that's what I'm looking for. I'm going to toss in the strontium chloride. Assuming the strontium chloride dissolves, that's going to add for us here some strontium ions, some chloride ions. Let's try to identify what's potentially the thing that's going to saturate, what's potentially the things that's going to precipitate. When we're doing our net ion equation, it's totally possible for you to get two solids that form. Again, for these math problems, there's always only going to be one solid. Now, I know sodium, again, is an alkali salt. It's soluble with everything. Sodium was happy being broken up with carbonate. Sodium will be perfectly happy. Table salt here dissolves no problem. The combination that's left for me here is, what about strontium and carbonate? Strontium may have been found with chloride, right? It's going to dissolve, break up, but maybe strontium carbonate that ends up forming a solid here. Let's check our charts here. Again, we check our solubility chart first. So we have, in this situation, a carbonate. So carbonate is way down here. Lo and behold here, yes, strontium and carbonate here is actually low soluble. That could potentially precipitate. The strontium chloride, where it started off, strontium and chloride was perfectly happy with it. That's when it's going to be soluble. Again, for a properly worded question, your reactants should always be aqueous to begin with. Okay, so realistically, what's happening is I'm taking SrCl2, I'm reacting with sodium carbonate. This one here is ending up forming my low soluble guy, strontium carbonate. It's double replacement, and I'm going to end up forming NaCl. I'll make sure to balance it this time here. Just a 2 that's needed there. All of these other guys were actually aqueous, right? But only this one here is a solid. We refer to that as a precipitate. This is why there's a limit. Why can't I just infinitely add in strontium here? Well, if I add in too much strontium chloride, if the Sr2 plus concentration gets high enough, it's going to be low soluble with carbonate. They're actually just going to precipitate out as strontium carbonate. So I do notice that strontium carbonate is actually a product, but before you write the saturation equation, before you write KSP, remember we always put the solid on the left side. Okay. So later on, what I'm going to need is I'm going to need to have, well, strontium carbonate here, the solid on the left side. This one, when it's saturated, when there's undissolved material present, it's going to constantly be breaking up to reform strontium and carbonate. But macroscopically, nothing changes because those microscopic reactions are occurring at the same rate. There's my dissolving equation, and I also write my KSP expression. KSP is basically KEQ. It's the product between the two soluble ions, strontium ions and carbonate ions, like that. Okay, two totally separate equations. All right. In this question here, is my strontium and the carbonate going to follow the mole ratio? Remember, there was two ways of making a saturated solution. One way, dissolving a solid, we just did, follows the mole ratio. As a solid breaks up, you have to form 1 to 1 to 1 as a ratio. Well, in this situation, wait a second. The strontium actually comes from strontium chloride. That comes from its own chemical. The carbonate was already present. That came from its own chemical here. I'm actually mixing two solutions together. Well, not quite a solution. I'm dropping a mass in. But because they were from two totally separate mixtures, these ones here, strontium and carbonate, come from different places, right? The strontium came from solid, SrCl2. The CO3 came from the solution of Na2CO3. So in this question here, there's no reason why these ones here would follow mole ratio. So what that says is I need to actually calculate these two numbers by themselves. Once I have these two numbers, you're more than welcome to just go over, just calculate KSP, which is what they're interested in. Okay. So let's do the easier one first. So if I have sodium carbonate, the concentration is 0.750. So let's take sodium carbonate. I'm going to write out the dissolving reaction here. So dissociates become two sodiums and carbonate. While the strontium carbonate salt doesn't follow the mole ratio, if I tell you you actually have 0.750 molar of the sodium carbonate, when it breaks up, this one here will follow mole ratio. I'm going to get 1.50 molar sodium. What I'm interested in is the carbonate, which came from a sodium carbonate, is actually 0.750. So this number is 0.750 molar because that came from this sodium carbonate. It's the mole ratio in the precipitate here isn't followed, but in this case here, as the salt dissociates, no doubt it has to be 1 to 1, 0.750. Now what's going to happen here is I'm going to try to figure out, well, how many grams of strontium would I need? Well, unfortunately here, it's actually, in this case here, going to be a molar. So in this case, what I'm going to do first, I'm going to set this here as x. Just because these are 1-to-1, we already decided it's not going to follow mole ratio. Let's see if we can backtrack and let's find out what the x is, and then maybe I can backtrack to find the mass of strontium chloride. Right? So if I have placeholder for these two here, I'm going to sub in. We're going to put in an x for strontium. The carbonate already was 0.750. That's the concentration. I'm going to assume that when you drop the mass here, the mass so fully dissolves that the total volume just stays as 15. So therefore, I don't need to worry about a dilution. What I would need is I need the KSP as a sort of test value. The KSP tells me when the product of the ions multiply to give this number, you're going to start precipitating out. We'll see this more in tomorrow's lesson as well. So let's go, well, we weren't given KSP in this question. Let's start off. We had already checked our first chart. Strontium carbonate here was low soluble. We had already predicted that's going to be solid. If we can't find an answer here, let's look on the bottom here. We have strontium carbonate here. All of these salts here are low soluble here. The KSP value I can read is actually 5.6 times 10 to the negative 10. So let's just take that from the table. This one here is 5.6 times 10 to the negative 10. Make a note to yourself, this one comes from the table. Right? If it's not on the table here, they probably give it in the question. Well, that's okay. This is one equation with one unknown. I can find out what x is. So let's figure out just x. X is the concentration of strontium here. Let's take 5.6 e negative 10, the KSP, divided by 0.75. I already knew the carbonate. The carbonate here was 7.5 times 10 to the negative 10. So what this says here is by the time the x reaches a concentration of 7.5 times 10 to the negative 10, when I multiply these two here, I've already hit this KSP. It's going to start precipitating. Well, what was the x? The x was actually the strontium that I got. Where did strontium come from? Strontium, again, I'm never going to have a bottle of just pure Sr plus 2. The strontium came from a solid SrCl2. When this guy breaks up, I get strontium ions, I get 2 chloride ions. If I now know the maximum amount that I can dissolve in is this 7.5 times 10 to the negative 10 number, this one here is molar. So therefore, how much salt can I have dissolved in? It's also 7.5 times 10 to the negative 10. Right? So I just wanted to just go over that again with you here. So far, we've been looking at sometimes forming saturated solutions, sometimes they follow mole ratio, sometimes it doesn't. In this case here, because the strontium and carbonate, because they came from two different places, they're not going to follow the mole ratio. But that's specific for the precipitate. The sodium carbonate, the salt, actually when it breaks up, that follows the mole ratio. Strontium chloride, that when it breaks up, that follows the mole ratio. That's not the mole ratio I'm talking about. I'm talking about the ion concentrations in the precipitate. Those don't necessarily follow the mole ratio. Okay? But nonetheless here, we've now found you can dissolve in 7.5 times 10 to the negative 10 molar of strontium chloride. Now finally we can use the volume again. Well, I only have 15 milliliters. Let's find out how many grams of strontium chloride given 15 milliliters, so 0.0150 liters. The concentration this strontium can hit is 7.5 times 10 to the negative 10. That's moles per liter. Anytime you need to get to grams, you just use molar mass. 1 mole is equal to, this is the molar mass of the whole compound strontium chloride. Strontium here is 87.6 plus twice chlorine, 35.5, is 158.6 grams. Okay, 0.015 times the 7.5 e negative 10 times 158.6, and this gives me here, how much mass can I toss in? 1.8 times 10 to the negative 9 grams. A really, really tiny amount because the salt here is very, very low soluble. Right? So you can frame that as this is the maximum amount I can toss in. As you add a smidgen of strontium chloride, that's going to have put in enough strontium, reacts with 0.75 molar of the carbonate. That's actually going to end up hitting the KSP limit. Again, we're going to do more in tomorrow's lesson. When you hit this KSP limit, that's when the precipitate starts forming. All right? So let me just try one more question with you here. Similar style of what's this maximum limit here before you hit saturation? I'm going to give you in this problem here the solubility of a compound manganese 2 iodate is given as 4.78 times 10 to the negative 3 molar. That is the solubility. That's how much you manage dissolving. First part of the question, let's say part A, I want you to calculate the KSP at this temperature. Right? So I have a table that's at 25 degrees because I totally made up this number. Chances are it's not going to match to the table. Once you know what the KSP is, then you can deal with this other problem here. What is the minimum? Right? Sure, I'm framing it as minimum, but it's just minimum to start precipitation. It's basically saying how much maximum can be in solution. What is the minimum Mn plus 2 required to just start precipitating? You've just hit this limit here. There's undissolved material. The equilibrium starts getting established. Just start precipitation from a 0.0200 molar KiO3 solution. Okay. Again, I encourage you just to pause the video so you can try it out for yourself. Part A of this question here is what we've been doing from earlier. They've already identified for you what potentially is a salt. If you know what the salt is, put the solid on the left side. MnIO3 dissolves to break out to become manganese ions and 2 iodate ions. I'm going to write out the KSP expression. The KSP is the products manganese multiplied by iodate. That 3 goes up into the power. I don't need to worry about divide by reactants because the reactants in these cases are always going to be solid. They gave me the solubility. Again, I'm going to remind you, solubility describes your solid. So in this case, your solubility is a number that goes here, 4.78 times 10 to the negative 3. Okay. If I'm starting off with this much solid here, the Mn and the iodate are going to follow the mole ratio. So the manganese here is going to be 4.78 times 10 to the negative 3. I'm going to double this number, 4.78 e negative 3 times 2. This gives me here 9.56 times 10 to the negative 3. So it follows the mole ratio as long as I assume it's dissolving. Anytime you have these two numbers, you can plug them directly into the KSP expression. So KSP here is equal to our 4.78 times 10 to the negative 3. The iodate here is 9.56 times 10 to the negative 3. Yes, I've already doubled it in following the mole ratio. I still have to square it because these are two separate equations. So what is the equilibrium constant supposed to be at this temperature? 4.78 e negative 3 times it by 9.56 e negative 3. Do that twice. And I'm getting a KSP value of 4.37 times 10 to the negative 7. All right. So if this were on the table here, it would just say manganese iodate, manganese 2 iodate. The limit is going to be 4.37 times 10 to the negative 7. By the time these ions multiply with the square, by the time it hits 4.37, that's when you saturate out. That's when you can't dissolve anymore. Now, armed with that KSP, we can do part B of the question. Sitting in front of you is some unknown volume, but I do know the concentration is 0.0200 molar KiO3. K is an alkali salt, so therefore I know the K plus and the iodate are just swimming around. The question here is, what is the minimum? What's the amount of manganese I can toss in before, when I multiply them, before I hit this limit, before the MnIO3 starts crystallizing and solidifying out again? All right. So let's just practice here. The KiO3 here, this one here is an alkali salt. This is a one-way arrow. This forms potassium and iodate. They give you the concentration of this to be 0.0200. Sure, this ends up forming 0.200 molar K plus, 0.0200 molar iodate. Even though I write it that way, it's understood that the solid is completely gone because the ions are just swimming around by themselves here. I'm going to toss in manganese here, a little bit easier from the earlier question. I don't have that counterbalancing negative ion. I just want to focus on the manganese. I want to know how much manganese can I toss in given the iodate that's already present. By the time when I multiply and I end up hitting this 4.37 number, I'm going to then crystallize out. So again, what I'm going to do here is, if I know what the solid is, even though I'm adding manganese and iodate as reactants, forming manganese 2 iodate as a product, I'm still going to put MnIO3 as a reactant. This is going to be in equilibrium with the manganese and the iodate. Again, 2 iodate there. I'm going to write the equilibrium expression and also write out the KSP expression. KSP is manganese times it by the iodate all squared. Okay. So what do I know? This time I'm mixing solutions. So this time I'm not dissolving the solid. I'm not going to follow the mole ratio. I already knew the iodate that was already in solution was 0.0200. Again, some people start getting confused here. Well, don't I need a times 2 here? Well, this 2 is only important if I follow the mole ratio. You already told me how much iodate there is. The 0.2 is how much 0.02 is how much I have. I don't know the manganese again. Let's put in an X. whenever you have those two placeholders here, you just put them directly into the KSP. I found the KSP from earlier, so 4.37 e negative 7. 4.37 times 10 to the negative 7. The manganese, this minimum amount before it starts precipitating, or the max amount you can dissolve, x times the iodate is 0.0200. Although I did not need to double it, I did not need to follow the mole ratio, I didn't start off from the solid, I do definitely need to square it. So that coefficient there ends up in the power there. I take this number, divide it by 0.02 all squared, and I end up getting x. X is equal to 1.09 times 10 to the negative 3. Always do yourself a favor and go back and reread the question. What were they after? They were interested in the concentration of manganese you can toss in. Perfect. X is the placeholder I put in for manganese. This is the very number I need to look for. So this one here, I'm going to write it in two ways. This is the minimum concentration of manganese added before it just starts precipitating. Or just to contrast that here, by the time you actually toss that in, this is also the maximum manganese dissolved in this 0.0200 molar iodate solution. So don't get sort of confused. Oh, why are they asking minimum one time or maximum one time? They're asking the same thing. They just want to sort of identify for you saturation has just happened. Basically, it'll follow the equilibrium ratios. It'll follow the KSP. And we're going to be using this KSP as a test value. Whenever these two things multiply, when the solubility product hits the solubility limit, that's when a precipitate will form. More on that tomorrow. Keep practicing your questions. So let me know if you have any problems. Thanks, guys.